So in this lecture, we shall continue with the theme of producing new topological spaces from old ones. So in the previous lecture, we saw that if X is a topological space, and if Y contained in X is a subset, then the topology on X induces a topology on Y, which we called the subspace topology. So in this lecture, we will see how to put a topology on the product of topological spaces. So let us prove the following lemma. Let X and Y be topological spaces. Let B contained in the power set of X cross Y be the collection of subsets defined as. So B is the collection U cross V, such that U is open in X and V is open in Y. So here we have denoted the topology on X by tau sub X and the topology on Y by tau sub Y. So then B satisfies the two conditions for generating a topology on X cross Y. So we are referring to the proposition which we proved in lecture 3. So let us begin by recalling the two conditions which is collection B needs to satisfy. So the first condition was that the union over all members of B should be the full set. So in this case, the full set is X cross Y. And the second condition is that suppose W1 and W2 are in B and X is an element of the intersection W1 intersection W2, then there is W in B such that X belongs to W and W is contained in W1 intersection W2. So it is clear that V satisfies condition A as X is in tau X and Y is in tau Y, and so X cross Y is itself in B. So therefore, when we take the union, one of these W's is X cross Y, and therefore this union is X cross Y. For the second condition, let us write W as U1 cross V1 and W2 as U2 cross V2. So where U1 comma U2 belong to are open in X and V1 comma V2 are open in Y. So if you make a picture, so W1 could be something like this. This is our X, let's say, and this is our Y. So this is going to be U1 and this is going to be V1. And our W2 could be something like this. So now suppose X is an element in W1 intersection W2, then X, since it's a point in X cross Y, it looks like A comma B, and this belongs to U1 cross V1 intersected with U2 cross V2. So this implies the point A is in U1 intersection U2 and the point B is in V1 intersection V2. So this implies that A comma B, this point, it belongs to U1 intersection U2 cross V1 intersection V2, which is contained in U1 cross V1 intersection U2 cross V2. So as tau x is a topology, it follows that the intersection is in tau x. And similarly, as tau y is a topology, the intersection v1 intersection v2 is in tau y. Thus, this set u1 intersection u2 cross v1 intersection v2 is contained in V. So this proves that V satisfies the condition small b. So now, using the proposition in lecture 3, it follows that B generates a topology tau on x cross y with basis b. So the same idea, so this completes the proof of the lemma. So this completes the proof of the lemma. So the same idea is about can be used to put a topology on the product. So this is an arbitrary product now instead of just two sets xi, where each xi is a topological space. So for example, if I is an infinite set, well, I mean, it doesn't matter what set I is. We can just take the collection the collection B, the collection of sets of this type such that UI is open in Xi. So this collection will satisfy the two conditions of the proposition. And so will generate a topology on this product Xi. So we make a very important remark here. So let us put that in red. So this topology is not a useful one. So this topology is called the box topology. Instead, on the product of an infinite, well, on an arbitrary product on an arbitrary product we define the collection of subsets B as is product I in I, ui. So the first condition is each ui is open in xi. And the second condition is all but finitely many ui's are equal to xi. So the second condition, this second condition, we can rewrite this as look at those j's. So the collection. So this condition is equivalent to this thing. The collection is same as, I'm just rephrasing it. I in I such that ui is not equal to xi is a finite set. So again, one checks easily that B satisfies the two conditions of the proposition which we referred to above, and so generates a topology on arbitrary product xi. So this topology is called the product topology. And the product topology is the one which is important to us, not the box topology. So we will see reasons for that later. So the following remarks, two remarks, are obvious. The first is when the index set is finite, then the box topology and the product topology are the same, are equal. And the second remark is when the index set is infinite, the box topology contains the product topology. In fact, the box topology in this case, that is when the index set is infinite, when there are infinitely many topological spaces and we are taking their product, is much larger than the product topology. So we also remark that the box topology will almost never be used in this course. Unless mentioned otherwise. A product of topological spaces will always be given the product topology. So now that we know the product topology, and the subspace topology, we have several examples. With us using these. So let us list a few. So we have R, R2, Rn, the complex numbers, we can take n copies of complex numbers. Then we can, yeah. Okay. We can take the circle S1, which is contained in the plane. So, and give the subspace topology with R2 having the standard topology. Similarly, we can construct the spheres Sn and again we give this the subspace topology from the standard topology on Rn plus 1. So the next example is we can take M and R. These are the set of n cross n matrices with real coefficients. So this is in bijection with Rn square, and so we can give it the product topology. So convince yourself that the basic open sets are of the type so these are matrices Aij's with Aij strictly less than some Cij and lying between Cij and Dij. Or let me rephrase this. So convince yourself that the collection the collection so we fix real numbers Cij strictly less than Dij for all I comma j lying between 1 and n, and we form this collection B is those matrices Aij's such that Aij lies between Cij and Dij. So this collection forms a basis for the topology on MNR. So inside MNR, there are several interesting subspaces which we are familiar with. There's those matrices. So the first one is GLNR, says that determinant of A is non-zero. So we can give this. So with give this the subspace topology. From MNR. And similarly, we have these examples. All these are interesting subsets of MNR, and we give all of them the subspace topology. This is the group of orthogonal matrices A transpose A is equal to identity. And finally, we have the special orthogonal matrices. These are orthogonal matrices whose determinant is 1. So similarly, we have so we saw this in the first discussion meeting. We put a topology on the complex numbers call this the standard topology. So thus, MNC, this is the set of n cross n matrices with complex coefficients is in bijection with Cn square, and so we can give this the product topology. And once again, convince yourself that the collection, so fix Rij is positive and B, so here, yeah, for every, yeah, okay, so this is Zij such that uh, okay, so maybe I should modify fix Rij's greater than 0, comma A ij in complex numbers. Let's write like this. Says that Aij is strictly less than Rij. So we are going to take our collect. So here Rij's and Aij's vary, and we collect all these subsets, and that collection is called B. So convince yourself that the collection forms a basis for the topology on MNC. Yeah, so in the same way, here also we allow Cij's and Dij's to vary, and for each pair Cij strictly less than Dij, we get subsets, and we take B to be the collection of all these subsets. So yeah, so maybe strictly speaking, I should write B is equal to this. Okay. And exactly as in the case of MNC, we have several familiar subsets. GNC is the set of all those matrices such that determinant of A is not 0. And this is given the subspace topology from MNC. Similarly, we have SLNC. And we have the unitary groups UN. There is those A in MNC such that A star A is equal to identity, and we have SUN. This is those A in question says that identity A is nu n and determinant of A is 1. So these are the special unitary matrices. So the S is for special. So now Yeah, so this is a list of several examples. And now that we have all these examples, we shall study continuous maps between these slash explore other topological properties. So we will end this lecture here.